right, so the first question in, well, June 2016 falls under radioactivity clearly. Well, when we're doing this question, when you have to plot the graph, because I'm sure they made you draw a graph, even without reading the rest of the question, the time will obviously go on the x-axis and the activity will go on the y-axis. Let us take a look at it. Oh, right. So in part A, they want you to draw the graph. So let's take a look at my solution. For the graph, there's someone scroll down to the black section. All right. How did your graph look? Something like this one here, from 80 and it kind of ends somewhere close to 5 there. Right? So, well, you notice what I did not do, right? I'm supposed to put the values next to each one here to get full marks in the exam, obviously, right? But I left that out by, well, I guess it's laziness on my part, right? So I'm hoping you have it. All right, now also, well, since this is a curve, in the exam, you have to draw the curve freehand. Do not use a ruler like I did here to get what? The curve. I was using a computer program and I didn't have the ability to get like a smooth curve. So I had to take what options was available. All right, so let's see what the next question is about. Right, so that's the graph paper they gave you to do it. All right, so this was pretty confusing. Let me explain why. In B part 1, they ask you to determine the half-life of the sample. Now, most people would read part 1, and when they finish part 1, they would read what? Part 2. But it almost seems if somebody were to ask me to find the half-life. Remember in the previous questions, and a few weeks ago, when we are finding the half-life, we usually do it 2 or 3 times and find the average. So that is what I would have done for part 1. But it seems that part 1 only wants you to take one value, and part 2 is the one that they want you to do it, what, 2 or 3 times and find what? The average. So I find that was badly stated, right? So anyway, let's try to find the half-life using one value, right? So let's see what we will get for the half-life. It started at what? 80. So how long did it take to drop to half its value? But you'll send your answers before I work it out. How long did it take to fall to half its value on average? Right? And let me see what the x-axis is measured in. Sorry, the y-axis, it's what? In seconds, right? So you have to make sure and put your units as well. Jordan, you say 1.6. It's in hours, you're sure? Somebody said it's in hours. I just double checking that. Oh, sorry. My mistake. It's in hours, Yes. Thank you, Nikeen, for correcting me there. All right. That's a big mistake. All right. So the rough average, and everybody's going to get something slightly different in the exam, right? That's expected. So it starts at 40. Sorry, it's 40. For me, it hits somewhere here, and then it scrolls down. Let's scroll down here. Let's scroll down, move downwards. And for me, right, it hitting on 1.6 hours. Now, some people have 1.5 hours. I doubt you're going to lose any marks for that in the exam. So by using one value and one value alone, right? But to be honest, I don't even think that is worth 5 marks. So that's overkill, right? So from using a graph, it's 1.6 hours, right? A question like this, if I had to give you this, I won't give you more than 2 marks, but CXC was being generous. So using a graph, determine a more accurate value. So what we're going to do, let's see how much half-lives we can get off the graph and then find the average. So the first half-life is 1.6. I'll write it somewhere here. So we have 1.6 for sure. So we at 40, how long will we take to half that? Well, half of 40 is 20. Let's go across, and then it went down. So on its third hour, right? On its third hour, you had 2 half-lives. But what's the time difference? The time taken for the next half-life is from 1.6 to 3. So we have to minus those 2 values. 3 minus 1.6 is 1.4 hours. So the next half-life took 1.4 hours, right? Not 3. I know some people might have said 3 by mistake, but it's the time difference in between the two. I think we could get another half-life. So let's get another half-life. We are 20. Well, half of 20 is what? 10. Right? Now remember, everybody's going to get slightly different values because when you're drawing a curve, everybody's hand is going to be slightly different. So if you get 1.5, is really not a problem. My next one happening at 4.6. So if this one is at 3 and this one is at 4.6, if we minus 3 and 4.6, so 4.6 minus 3, I'm getting what? Another 1.6. Do you think it's possible to get another half-life? I think it's possible. I think it's just possible. So half of 10 is 5. And look at it. We just get it here. So we're lucky. And this one lands on what? 6. So this one is what? 4.6. And this one is what? 6. Let's find the time difference. 6 minus 4.6. I'm getting 1.4. So we can find the average of all of these half-lives. Now, you might get something slightly different. I'm going to keep saying it over and over. You don't have to worry. Once it's very, very close to what I have. So let me add up all of those. 1.6 plus 1.4 plus 1.6 plus 1.4 divided by 4. I am getting 1.5 hours. That is what I am getting. Right? Look how much more work we had to do for part 2. And we got 6 marks. I'm not too sure why that is so, right? Right, so to get full marks in the exam, you have to show all your lines on the graph. You have to show them how you find the average. Well, when you're finding the time difference between the two of them, make sure you show it here, right? You have to say 3 minus 1.6 and show them you get the 1.4 hours. Show them every piece of working to show that you're working for that 6 marks, right? Don't miss out anything. That is what I advise. Okay, and make sure and put all your units and everything. All right, so how much? Oh, I did, sorry. What did I put? Oh, sorry, I made a small mistake. Divided by 4. Another mistake. Sorry about that, guys. All right. So how much of y'all on track so far? That you got approximately 1.5 and you did 4 pieces of working. Right. So people are saying yes, yes. Good so far, good so far. All right. From your graph and using dotted lines, determine how long it takes for the activity of the sample to be reduced to 10 disintegrations per second. Well, this is going to be super easy. We just happen to have it here already, right? The time it takes is what? For me, it's 4.6 hours, but I think they told us to use what? Dotted lines. So make sure when you're doing it in the exam, you use a little dash or dotted lines like this. All right. Nikin, if you got 5, I think that's a little too off. I'm pretty sure the answer is not 5. I'm real sure it's not 5. It's supposed to be around 4.6 or 4.5. Right? So for me, I'm putting what I got 4.6, and I'm going to put the hours, and I will put my dash lines for the examiner. Right. State one reason why a line drawn through all points would not form a perfectly smooth curve. Well, this is an experiment, right? We gotta use our imagination here. Isn't it possible that we have errors? Angelo, 4.4, nothing wrong with 4.4. We could use 4.4. I would give you full marks for that in the exam, right? So it's an experiment, right? Now, when you're doing a radioactivity experiment, let's say that you have a sample here. So this is your sample, your radioactive rock. So radioactivity is going to be coming out of the rock. Now you are going to use an instrument called a GM tube, a Geiger-Müller tube, to measure the amount of radioactivity. But in real life, right, there's something called background radiation. Right now, where you are sitting, there's background radiation, meaning that, remember, the Earth contains radioactive materials. So the radioactive materials in the ground itself or around you will affect, because some of that will reach the Geiger-Müller tube. So you're measuring two things here now. You're measuring the actual radiation of the sample in the lab, but then the background radiation gets mixed into it. Now, usually background radiation is small, but it still can register on a GM tube, right? Or a Geiger-Müller tube. So let's see if I, right? And there's another reason, right? The reason you might not get a smooth curve, because remember, radioactivity is a random process. Remember, we went through, it's random in two ways. The actual atoms that decay, you cannot predict which half will decay, and you cannot predict when it will decay within the half-life. So that will affect you getting a perfectly smooth curve. So there were two answers for that one. I want everyone to write the two answers. It could be because of the random nature of radioactivity, of radioactive decay, or the background radiation could have been affected. They only ask for one. You take down both of them, and on the day of the exam, you just choose one. Pause that there. All right, so let's move on, right? So part E, all elements, including radioactive substances, have an atomic number and a mass number. Now this falls under more what? Chemistry. So if you're doing chemistry, this is going to be what? A super easy question. I've already prepared this, right? We all know the atomic number, which we usually denote with the letter Z, is the amount of what? Protons. And the mass number, which is usually what? Capital A, is what? The sum of the protons and neutrons, right? If you did not get this correct, but I suspect everybody in today's class got it correct, just take it down. I'll give you a 20 seconds, well, a 30 seconds for it, okay? But I have nothing to do for the next 30 seconds, so I guess you could just let me know if you got it right or if you got it wrong. Let's see what's next on the list. All right, so in medicine, well, in medicine, they usually use a lot of radioisotopes. They're pretty popular in the treatment of cancer and whatnot, right? They can also be used to check the functionality of someone's thyroid. What does the 123 represent? Well, this is an easy answer because you're using part E to help you with that. The 123 is what? The mass number, which represents what? The total of protons and neutrons. So you're almost rewriting this same answer here, but you just use the word 123, right? To me, this question was super easy for 25 marks. How much of you all think you will have gotten at least 20 of those 25 marks. Like you're confident that you're coming out with 20 or more marks there. All right. So you see, physics not really that hard, right? So let's move on. Let's take a look at the next question here. So let me just scroll through. Right. All right. So I'm going to give you a 10 minutes with question 2, only question 2. For part 1, the correct answer here is the Newton, right? But I want to explain this in a little more detail, right? We know force is measured in newtons. Now, if they said SI unit. Now, if they had changed that question to this, let me say they said, instead of SI unit, they said SI base units. Just in case now, it comes a little different in your exam. And they ask you the same question for force. If you put newtons, you would actually get that wrong. Base units means that you want your answer in its simplest form, the simplest units, made up of one or a mixture of the 7 basic SI units, like kilograms, meters, time, like seconds and whatnot. So to get that, you would actually have to use this formula. Force is mass multiplied by acceleration. Remember, that's a real basic formula in physics. So that means to calculate force, mass is in kilograms, but acceleration is meters per second squared. Now you notice all of these have basic SI units, kilograms, meters per seconds. So if they ask for the SI base units of newtons, you have to put kilograms, meters per second squared. But they didn't ask for that. I'm just saying if that comes for your exam. And the other one here, well, I think most people got this correct. Some people send their answers. Remember, momentum is mass multiplied by velocity. Mass is in kilograms and velocity is meters per second. So you're supposed to put kilograms, meters per second. Right, so I suspect that everyone got this one correct. Real people supposed to know B part 1. Number Newton has 3 laws of motion, and there are many different wordings of it. But this is the one I put, right? Newton's third law states that there's Newton's third law of motion, I should put of motion here, right? States that there is an equal and opposite reaction for every action. Like I said, there are slightly different wordings of it. Go in 10 different textbooks, they will word it slightly different. At the end of the day, if you push on something, it will push back at you. And not in today's exam, but in your exam, they can ask you for an example of Newton's third law. So I have 2 examples here. Make sure and take down the 2 examples in case you are the unlucky people to get that question in the exam, right? So take a half a minute and take down everything here as well. Let's see what the next part of the question is. So that's 3 marks there. That's easy stuff. All right. So but everyone would have read the question by now. So a plane is flying horizontally, right? So that means it's not moving upwards, it's not moving downwards, right? Horizontal. How this works, right? Remember, if I have a proper diagram just now, right? But if this is the plane, right? There's a terrible drawing of a plane there, right? Remember, the boosters or the turbines or whatnot are pushing air this direction, right? From the turbines in the plane. And of course, that causes what? A forward motion. In other words, Newton's what? Third law, right? So let's see how we can word that properly for the examiner. Here's a proper diagram, right? But this is exactly what I said here, but with proper wording, right? So read it first and then take it down, because I'm pretty sure everybody could have imagined it. They knew this was Newton's third law. But when it's time to word it in the exam, well, that's a different story, right? All right, so that should be more than enough time. All right, so that's part 2, 4 marks. So 4 marks, I think that was word 4 marks. Well, define linear momentum. All right, so let's see what, remember momentum is what? Mass by velocity. They didn't ask you for the conservation of momentum. The conservation of momentum means the momentum before the collision is equal to the total momentum just after the collision. This is all they're basically looking for. Linear momentum is a vector quantity, which means direction is super important. And it's just defined as the mass of the object, which is usually represented by m multiplied by its velocity, which is v, right? Even if you don't include the letter m and the letter v, you're going to get full marks in the exam, all right? So I'm pretty sure everyone here had something very close to this, but I'll still give you 20 seconds to take down my definition. And then on the day of the exam, you can choose between your definition and my definition. All right, finally, a calculation question. Simple joys in life. Okay, so let's see what we have here. So it looks like in this question, it's going to be a conservation of momentum question. It seems to have no tricks in the units. They give you things like kilograms and meters per second. All right, so yeah, let's draw out this situation. You have one ball, right, which is 8 kilograms, and it's moving east at 10 meters per second. Then you have another ball moving the opposite direction. Instead, it's west, right? So it's 2 kilograms and it's moving west at 5 meters per second. Now remember, velocity and momentum are vector quantities. So we're going to have to assign signs to these velocities, right? So we're going to choose east to be positive. So we're going to put this as positive what? 10. And since the other ball is going the complete opposite direction, I'm going to put -5 as the velocity. Now, after the collision, the both of them combine, apparently. They smash into each other. So that means the total mass after collision, because they smashed into each other, will obviously be what? 10 kilograms. 8 plus 2 is 10. We just don't know the velocity this mess is moving at. When we calculate the velocity, if we get a negative value, that means it's going this way. If we get a positive value, it means it's going east. So let's calculate the momentum before collision. 8 mass by velocity, so 8 by 10 plus 2 by -5 is equal to, after the collision, 10 multiplied by what? V. 8 by 10 is 80. 2 by -5 is -10 is equal to 10V. This is 70 is equal to 10V. And we get V as what? So across, well, the multiply, you get a divide. So 7 meters per second, and it's positive. So that means it's going this, and the direction is what? East. How much of you all got that? 7 meters per second, and it was going east. Right, Abigail, Liana, Zachary, great. If you didn't, well, it's on the screen. So take a minute and draw everything properly if you didn't get it out and whatnot. All right, so let's look at question 3 and see what topic this is at least, right? All right. So question 3 seems to be about heat and what is the formulas mean, and have a little calculation, right? All right, so get started on this one. Please don't mix up latent heat with specific heat capacity questions. Latent heat is when there's no change in temperature, only a change in state. But things like when you see specific heat capacity, that means there's a change in temperature, but it remains the same state. Right, so I put some time on this one. All right, I think that's enough time to try that question. Well, this is a basic formula. Let's see if I had written the answer for that out. Right. So you might have slightly different wording. I just gave a very detailed answer. It stands for the energy, the heat energy. C, common C, is the specific heat capacity. Remember, the capital C is heat capacity, right? The truth is, the SI units, right, is joules per kilogram Kelvin. I know some people have joules per kilogram degrees Celsius. This is also regarded as correct in the exam. But if they're asking for the SI unit, to be safe, use Kelvin, because the SI unit for temperature is not degrees Celsius. It's actually Kelvin. All right. And remember, this is change. When you're doing these types of questions, you have to calculate the change in temperature. Well, whether you have it in Kelvin or degrees Celsius, well, when you find the change in temperature, you're going to get the same value, right? So the change in temperature, the SI unit is usually Kelvin, not usually, it is Kelvin, right? On the letter L, is the specific latent heat, whose unit is what? Joules per kilogram. All right. So if you need to take down my definitions here, I'll give you a minute, right? I suspect everybody's going to have something really, really, really similar, but you might have the SI unit wrong. All right, so I think I answered the other one here, part B already. L is what? The latent heat. Now, they didn't already say, this is L, right? They didn't say whether it was L subscript V or L subscript F. Remember, when it's V, it's latent heat of vaporization. And if it's common F, it's what? Latent heat of fusion. But they didn't specify which one, so I just put latent heat. All right, so let's see what's going on with part C, but I just want to scroll down to see if they give us any information, what they usually do at the end of the question. Now, notice what they did. The specific heat capacity of water, they gave us it as 4.2, but they use grams, not kilograms. So that means when we're doing the calculations today, we're going to be working in grams, not kilograms. So you have to be real careful about that, right? So you notice in the question they gave us grams. So we're not going to convert anything. So quick question, right? Let me explain what's going on here, right? I was drawing up the diagram while you were doing the question. You have some ice. You're going to throw it into the water. Now, obviously, ice makes water cooler. So if the initial temperature of the water was 30 degrees Celsius, when you throw the ice in, it's supposed to get a little bit colder. And it did. It went from 30 to 20, which is the job of the ice, I guess. What's going to happen here isn't the temperature of the water dropping, which means the water is losing energy, because the higher the temperature, the more energy it has. Energy lost is equal to energy gain. So if something is losing energy, well, then something else is gaining energy. So here's the thing. The heat lost by the water was given to the ice. Now, here's the thing. The ice would first have to change from ice to water. It would have to change state. And then when the ice now melts, well, you have new water because the ice just melts. The ice would be, the new water would be at 0 degrees Celsius. And now, remember, everything here has an equilibrium temperature of 20 degrees. So the ice would have, which is just melted, would have to go from 0 degrees Celsius and raise to a temperature of 20 degrees Celsius. Right now, I'm going to do the full calculation and then do the, I know they break it up into small pieces, but we'll fill in that after. Who can tell me what was the mass of the ice? Well, we know the water is 100 grams, the initial water, which was at 30 degrees. But how much is the ice? They never really came out right and said the mass of the ice. There is a little bit of common sense here. How much was the mass of the ice? Jordan, correct. Nikki, Abigail, I'll take one more answer, also correct, and Tyrisha. It has to be 10 grams, right? Because if the water was 100, and then after the whole scenario, it increased by 10, but then the mass of the ice had to be 10. So it was 10 grams of ice. So remember, let's calculate the heat lost by the water. Now, when they say the water here, they're talking about the initial water, right? Not the new water being introduced by the melted ice. So the water is cooling down. It's going from 30 to 20. So there's no change in state. It's water, and now it's just cooler water. So to calculate the heat energy here, right, we have to use this formula, which is what? Mass by specific heat capacity by the change in temperature. So the mass of the initial water was 100 grams. The specific heat capacity was 4.2. And the change in temperature is 10 because it went from 30 to 20. You just minus both of them. So let's calculate this and see how much we get. 100 multiplied by 4.2 multiplied by 10. I got 4,200 joules, right? So this energy now was given up to melt the ice and to raise its temperature to 20 degrees. Let's calculate how much energy it took to melt the ice from, in other words, just change it from a solid to a liquid. But that seems to me there's a change in state because ice is solid and water is what? A liquid. So you have to use this formula now. You have to use the energy, I think it's this formula they were referring to, right? The mass of the ice multiplied by the latent heat of fusion of the ice. There's no change in temperature. So it's just what? The mass of the ice, which is 10, but we don't know common L. That's the aim of the question. So it's just 10 L plus, we have to raise the temperature of the new water, right? From 0 all the way to 20. Now that seems like no change in state because it's cold water changing to slightly warmer water. So let's see what we get here. We have to use this formula again. EH is equal to mass by C by change in temperature. The mass of this new water is 10. It's water, so the specific heat capacity is 4.2, and the change in temperature is 20. It went from 0 to 20. Let's calculate that. 10 by 4.2 by 20, 840. Don't you all think you could easily solve for L, right? Solve for L and tell me what you get for L. And that value will be what? The latent heat of fusion of ice. And its unit will be joules per gram, not kilogram today, joules per gram. Solving for L, So you're just trying to get L on one side and everybody else on the other side. So you throw across the positive 840, you get minus 840, right? I think a few people forgot when you throw across a positive, you get what? A negative. And here you'll get 3360. The 10 is a multiply, throw it across. So from here it's pretty obvious. 336 joules per gram. Right? So that's, and of course, they ask you to break it up into parts now, right? You see how we did the whole calculation there. But we are filling all the answers piece by piece just now. Let's give everyone like a 30 seconds to take down the working. Let's see. Calculate the heat lost by the water. The heat lost by the water would have been what? The 4200. So that working over here, the working that we did in red here would go over here. And the other one, calculate the heat gained by the melted ice. There's no real calculation here, no, right? The heat gained by the ice was equal to the heat lost by the water, right? Remember, heat loss is equal to what? Heat gain. So all you had to do was just write back a sentence. The heat lost by the water is equal to what? The heat gained by the ice. And the answer would have been what? 4200 joules again, right? The same value over here. And then for the next part, right? This is where they ask you to calculate everything, right? So you just had to write down everything we just did here in red, green, and purple, and then solve the equation and whatnot. Okay? Right. Now this one was worth 15 marks, right? I think a lot of you all will have gotten the last part wrong, right? Sorry, Jordan. Somebody said it was orange. It wasn't red. Let me watch that again. It's red. What are you talking about? Well, all right. Okay. How much of you all, to be honest, that you got more than 10? Look at it. This part was worth 3 marks. This part was worth 2. And this part was worth 3. So if you got this whole part C wrong, you're going to get less than 10. Oh, Xavier, I think you got full. Nikin, you said you get a little more than 10, right? 18 is it? Can we 18? Oh, God. Let's call it 18. 18, sorry. Less than 10. And Nikin, you said you got. All right, so but if you get wrong, at least you know what you did wrong. No, okay. We still have more practice, guys. We still have about 3 more weeks. We're going to reach there. We're going to reach there. Let's see what the next question is about there. All right, so part 4, just give it a read. I think we could do this one together. I already prepared the answer for this one, right? They're asking you about electromagnetic waves. They're not even asking about all the electromagnetic waves. So all the electromagnetic waves would be things like what? Gamma, X-rays, UV, visible, infrared, microwaves, radio waves. They only want you to name 3 out of all of them, right? But they want it in increasing wavelength. So you could choose any 3 that you want. Just make sure you start from the smallest wavelength and you gradually increase. And you want some uses of each one. So I already prepared this for you guys in advance. Look at over here, right? So I just telling you, in the exam, if they ask me to put 3 in increasing wavelength, I would just start from gamma. I will list him first because he has the smallest wavelength, followed by X-rays, followed by ultraviolet, right? I'll just list those 3. And look, I have the uses here laid out for you already. Right? This might take a little too long to, tell what, I'll give you all 5 minutes to take it on, right? You don't have to draw the diagram if you don't want to. I think you all already have this diagram, all right? But you think you can take down the uses at least and learn them off for the exam. So take our 5 minutes and we will move on. All right, so let's learn off the uses. And of course, you just have to basically remember the order of the electromagnetic spectrum. Gamma has the smallest wavelength, but the highest frequency, while radio waves have the largest wavelength. Sorry, and the smallest frequency. Wavelength and frequency are opposites in the electromagnetic spectrum. Let's see what the next part is about. This was worth 6 marks, right? So if you never learned that off, like 6 marks going in the exam. All right, so you have some calculations here. Believe me, this calculation, even though they put 5 marks here, it was super easy. Way easier than you think. You just have to be able to type in these numbers properly on the calculator. All right, so take 2 minutes. Okay. For the rattlesnake, well, in both cases, right, the velocity is going to be the same, right? Because all waves in the electromagnetic spectrum have the same what? Wavelength. So for both of them, it's 3 multiplied by 10 to the power 8, which was given to you by the examiner, right? This is in meters per second. And you just have to divide it by what? The corresponding frequency, well, which the examiner gave you straight out. Right, and frequency is measured in hertz, and for the honeybee, it's how much? 1 multiplied by 10 to the power 15 hertz. Right, so let's just divide these two and divide these two and get the answer. And that's pretty much it. So, unless some of you might be a little interested in seeing it on the calculator. So let's see. 3 EXP 8. You notice when I press the EXP button, the multiply by 10 automatically comes on the screen. You just have to type in the 8. And you divide it by 3.5 EXP 14. How much of y'all got that for the first one, right? You're getting 1 0 there. If you put it in standard form, 1, 2, 3, 4, 5, 6, 7. 8.57 multiplied by 10 to the power minus 7 meters. Right. And for the next one, it's the same basic thing, nothing, that's a type of thing, I guess. So 3 EXP 8, right? Divided by 1 EXP 15. And this is what we get here. 1, 2, 3, 4, 5, 6, 7, right? So this one here is what? 3 multiplied by 10 to the power minus 7 meters. How much people got both correct? You don't have to put it in standard form. It just looks nicer than putting all of those zeros in front. Okay. Look at how much marks this is worth, 5. I mean, and some other things which are much less work. I find this should have been 6 or 7 marks rather than 5. Anyway, part C, do not overthink it. Remember, well, when you see lightning, right now, lightning is what? When you see it, that's the light moving. Light is so much faster than sound, like so much faster. That's why you see the lightning first, and then hear it, better known as what? Thunder. Believe me, this is the formula you're using. Distance is speed multiplied by time, right? So if the thunder is heard 2.3 seconds after the flash, that means the time the sound takes to travel is 2.3 seconds. If the lightning strike is 750, they just give it, this is straight out. I don't know why this is worth 4 marks, right? The distance is 750. You're trying to calculate the speed and they give you the time. It is throw across the multiply to get a divide. So I think everyone could do this for me and put the correct units. Right, so. And I am getting 326.09 meters per second. I guess we shouldn't complain. 15 marks there again, guys, right? That's the end of question 4. All right, guys, so I think we didn't take a break today and it's almost 1:20. Right, so I was hoping to reach the end of the past paper, but I still think we need a 45 minutes because the next 2 questions have a lot of calculations and they have a considerable amount of notes. So guys, I will end off class here today, and next week we will do questions 5 and 6, and I will start preparing the next past paper, which I think is 2017. I'll just choose one, right? And I will write, it will be just like today, where you try the question first, and then I jump in with the answers. So guys, take care, enjoy, well, today's Mother's Day, so, have a good one, and I will see you all this week. Take care, guys.